Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. We all know that smell is chemistry. When you perceive the sharp zest of a lemon or the earthy aroma of coffee, you are experiencing the direct binding of odorant molecules to specific protein receptors inside your nose. For decades, the dominant model was simple: the lock and key theory. The shape of the molecule dictates the smell. But science, as always, is far more complex. What if the identity of a molecule, its smell, isn't just defined by its static shape, but by how much it wiggles? And what if that wiggling is controlled almost entirely by temperature? Welcome to the world of thermal olfaction, where every degree counts, and the theoretical limit is the absolute zero sniff. To understand this, we must first recognize that temperature is, fundamentally, molecular motion. The colder a substance gets, approaching that frigid limit of absolute zero, the slower and more stable its constituent atoms become. Their chemical bonds are rigid, their conformation fixed. As temperature rises, thermal energy translates into furious, internal vibration, causing molecules to stretch, bend, and twist millions of times per second. This thermal dissonance is key to scent. When an odorant molecule enters your nasal cavity, it must dock into a highly specialized olfactory receptor. If the odorant molecule is hot and vibrating wildly, its dynamic shape might momentarily shift enough to fit into a receptor pocket it couldn't normally access. Conversely, if it is supercooled, its rigid, low-energy state might make it too stiff, or too geometrically fixed, to establish the necessary transient interactions with the receptor protein. Think about serving food. A perfectly chilled glass of white wine has a subtle, nuanced bouquet. But if you warm that wine, its scent explodes. This isn't just about diffusion. It's about the wine's complex esters and terpenes gaining the thermal energy required to present a different vibrational signature to your nose. The molecules themselves have changed their smell identity based on their thermal state. But the odorant is only half of the story. The receptor itself, the protein embedded in the cell membrane, is also a dynamic entity. Proteins are not static scaffolds. They are constantly changing shape in response to their environment. This phenomenon is called protein dynamics. Low temperatures stabilize the protein structure, making the receptor pocket tight and unforgiving, acting like a strict gatekeeper. Higher temperatures introduce flexibility, allowing the receptor pocket to breathe and slightly deform, perhaps allowing a better fit for a wider range of odorants, or conversely, a worse fit if the protein becomes too unstable. Imagine a lock whose internal mechanisms shift slightly based on the room temperature. The same key might work perfectly at 25 degrees Celsius, but fail entirely at 5 degrees. This is the thermal fine-tuning that dictates whether or not a signal reaches your brain. Our nose is, effectively, acting as a highly sensitive thermometer, sensing not just the static chemistry of a substance, but its thermodynamic state. This concept becomes even more profound when we consider the controversial yet compelling vibrational theory of olfaction. This theory suggests that we don't just smell shape, we smell the specific energy frequencies, vibrations, of a molecule's bonds. In this model, the olfactory receptor acts like a spectrometer, detecting the quantum vibrations of the odorant. If the vibrational theory holds true, then temperature is the ultimate controller. The closer we get to absolute zero, the more precise and predictable those quantum vibrations become, removing the thermal noise that usually blurs molecular signatures. The absolute zero sniff represents the theoretical moment where the purest, most rigid chemical identity is presented to the sensory system, stripped of all thermal ambiguity. It is the moment the molecule's fundamental energy signature is revealed. Experimentally, scientists have used isotopic substitution, swapping hydrogen for its heavier cousin, deuterium, to test this. Deuterium bonds vibrate at a different frequency than hydrogen bonds, but the shape of the molecule remains almost identical. Under classical shape theory, the smell shouldn't change. Yet, certain deuterated molecules smell noticeably different, confirming that vibrational dynamics, driven by thermal energy, play a crucial role in the recognition process. So the next time you wonder why the fresh mountain air smells faint but crisp, or why that frozen orange juice concentrate has virtually no aroma, remember this. You're witnessing a delicate dance between chemistry and physics, where heat is the conductor, and molecular vibration is the melody that defines every single scent we perceive. Our ability to smell is a constant negotiation with the laws of thermodynamics. For more incredible facts like this, don't forget to subscribe and turn on notifications.